In this video, we go over the algorithm for EM and some idea about why the algorithms work. As we have seen in class, there are a lot of situations that involve missing data or latent variables, where the complete data log likelihood, including both the observed and the missing data, is much easier to maximize and take the derivative to compared to the observed data log likelihood, which usually involves either integration over continuous missing data or summation over discrete missing data. The EM algorithm maximizes the observed data log likelihood iteratively, and it alternates between two steps. The first step is known as a E step, where E stands for expectation. The idea is that we're going to compute the expectation of the complete data log likelihood given by L of theta, given both the observed and the missing data. And this is given the observed data and the current parameter estimates, which we call theta old. So theta old here is usually your theta estimates from the last iteration, just like our theta case in the case of optimizations. Okay. So let's denote this expectation of the log likelihood of theta given the complete data by Q, where you can see that the variable inside is actually theta, but because we are looking at the conditional expectation of this with respect to what is the distribution of the missing data, given the observed data and the last iteration's theta old, we have both theta and theta vod involved in this Q function. So by definition, this expectation is the integral over the conditional distribution of the missing data, given the observed data and the last iteration's theta old. So under this conditional distribution, what is the log likelihood of the complete data? Once we have this thing in the E step, we can see that this is actually a function that only involves theta, right? Essentially, theta old is fixed because we got it from the last iteration. Our observed data is fixed, and that essentially determines what is the conditional distribution of the missing data. And the only variables left in this function is actually theta. And in the M step, what we do is we are going to try to find the theta values that maximizes this Q function in the first step. In other words, we're going to play with different possibilities of the theta here and see which combination makes the Q largest. And we're going to make that our theta new. So our new iterations theta is going to be given by whatever theta value that maximizes this Q function. Lastly, we update our theta old to be the theta new we just got. So you can see that in each iteration, we actually first take the E step to find the Q function. We find the new thetas that maximize the Q function, and that is going to be our new guess to what the parameter estimates are going to be. And usually we iterate the EM algorithm for a large number of cycles, like 500 or 1000, or until you reach some kind of tolerance. So there are a few remarks I'd like to give about the EM algorithm. The first is that under quite general conditions, it can be shown that the sequence of thetas that we obtain from the EM algorithm is guaranteed to converge to a local maximum. And again, a local maximum does not guarantee a global maximum, right? So if you suspect that your problem is actually non-convex, then in this case, there might be multiple local maxima depending on your starting value. In these situations, it is advised for you to run the EM algorithm with different starting points, so with different initial theta olds, and see whether they end up at the same point. If they don't, maybe you run it for a large number of starting points and choose the global maxima out of all of the local ones. We're not going to provide a proof of why the EM algorithm works, but I do want to give you some general intuitions about why one iteration of the EM algorithm is expected to somewhat improve the observed data log likelihood when you replace the theta old with the new estimate theta new that optimizes the Q function. If you're interested in a complete proof, I am including a link over here in the footnote. That is the link to Jeff Wu's 1983 paper. Okay. To show why the EM algorithm works intuitively, I want to discuss the non-decreasing Q function. So for notational simplicity, let's not use X observe and X miss anymore. And let's simply suppose that our observed data is called X and our missing data is called Y. Okay. All right. So you should note that the observed data log likelihood, which is L of theta given X, our observed data, is essentially the log of this marginal probability that we observe the X's, given all possibilities of the Y, the missing data. So essentially, you integrate over the distribution of Y, the joint density of our observed data and missing data given our parameter theta. So this thing on the right-hand side is actually equal to what's on the second line because you can always divide and multiply something it's the same thing, and that doesn't change it, right? So let's suppose that we are going to divide it by f of y given theta and theta ot, and also multiply it by this thing. So what is this blue thing that we're multiplying and dividing over here? It's actually given the observed data and the current estimates to theta. What is the conditional distribution of your missing data given these two things? And you can see that by definition, the thing on the second line is essentially the log of the expectation of this fraction over here over this later density. So essentially, it is the expectation of this ratio between the joint distribution of x and y given theta and the conditional distribution of y given x and the old theta we had from the last iteration under the conditional distribution of y given the observed data and theta old. All right, so now I wanted you to remember something you learned in Stat 410, which is Jensen's inequality. It says that for a concave function, such as the log function, the function applied to the expectation is going to be larger than and equal to the expectation of that function, right? So that means that our log of the expectation on the third line is going to be greater than or equal to the expectation of the log of the same thing over here. All right, so we know that log of this ratio over here can be broken down into log of fxy given theta minus log of fy given x and theta old, right? So log of the numerator minus the log of the denominator. We know that expectation, when you do like expectation of subtractions or sums, you can break it into the sum or subtraction of expectations, right? So what we had on the last line is essentially equal to the expectation of the log of fxy given theta, conditioning on theta and theta old, meaning that if we look at the conditional distribution of y given the observed theta and theta old, the expectation of the log of this joint distribution, right? Minus this later term, which is essentially the denominator, right? The conditional expectation of the log of fy given x and theta old. Okay, so let's take a look at this blue part. It turns out this blue part is essentially the Q function that we get from the E step. So by definition, we know that this is the same as Q theta and theta old, where theta old is fixed because we know what were our theta estimates from the last iteration, and theta is the thing that varies and changes the value of Q, right? This red term is just this thing on the right, and that's actually something that does not involve theta. So you can see that this red term over here, it does not involve theta, meaning that when you change the theta value, this thing is not going to change. Let's recall that in the EM algorithm, in each step, we first find the Q function, and then we look for theta that makes Q as large as possible, right? What that means is that when you get the theta nu, which is something that maximizes the Q function, it's bound to be greater than or equal to Q evaluated at any other possible theta, And one of them is the Q calculated at theta old, right? What that means intuitively is that when you run one iteration of EM, because you're trying to improve your theta into theta nu, which maximizes this Q, and this later term doesn't change, the right-hand side of this whole inequality does not decrease with one iteration of EM. Intuitively, it means that with one iteration, it is expected that most of the time, your log likelihood of the observed data is going to get better when you choose the new estimates.